There are several considerations that we should take when we think about gravity and orbits. And sometimes we can see in movies or real pictures astronauts floating, and some people referring to this as zero G, as in we're not experiencing any gravity. This is, of course, not really the case, and we can very easily demonstrate this because if we think about putting things which are further and further away, you are actually experiencing lower gravity. So if you double the distance, you get 1/4 of the force. If you triple the distance, you get 1/9 of the force. Very easily, and let's say that you believe that there's zero gravity in the International Space Station, you can actually check this in a quantitative way. A way to do it is to write down the radius you'd put into Newton's equation as the radius of the Earth plus the height. This will be the height that the International Space Station is at, which is about 400 kilometers. And you can actually have a look at the ratio, for example, of the gravity force at that point versus the gravity force at the Earth's surface. And you can very easily demonstrate that this is not zero. So you still feel about 90% of the gravity on Earth, even at the height of the International Space Station. So what we typically refer to as zero gravity is not really zero gravity, but it's just essentially an orbital phenomena. It's the fact that astronauts and the International Space Station are essentially falling down at the same rate, and therefore, relative to the International Space Station, it feels like there's no force, but that's because both of them are falling. Now, talking about gravity and orbits requires us, if we want to classify them and put them into groups, to look at, for example, gravitational potential energy and kinetic energy. And again, I assume that this is a quick recap. I'll just go through it in case you forgot from last year or previous years because the world has gone mad. So what you do is you understand that whenever you're talking about an orbit, the dominating force will be gravity. And in Newton's form, this is just G m big M small m over r squared. And we can define gravitational potential energy U in a way that the change from the initial to final position is just given by the integral over here. Now, if the gravitational force is due to a mass big M at the origin, with F acting downwards, and this is important because gravity is a central force, and dr pointing radially outwards, then the dot product simply becomes minus f dr. And this allows us to write the integral in a much simpler form, which is just g m small m with a minus, and then the difference between 1 over the final position and minus 1 over the initial position. And the standard way that we deal with this is to define essentially a point at which the gravitational potential energy is zero, and we do that by setting this final radius rf to be infinity. If we do this, then we can write that gravitational potential energy is in the form that is familiar to you, which is just minus g big M small m over r. And this is important when we look at the classical total energy, which is crucial to define escape velocity. If you want to send things away from the Earth or even away from the solar system, we need to understand what velocity and how much energy we require. Now, in a classical way, we can say that the total mechanical energy of a body of mass m that you want to send to space, for example, is simply the sum of the kinetic energy, which is 1/2 mv squared, plus the potential gravitational energy, which we've defined as minus gmm over r. Now, say that we want to remove this object to infinity, such that its gravitational pull, the body of big mass m, like the Earth or the Sun, can no longer kind of keep it bound. So essentially, we want to make the system unbound. And if we do that, the minimum kinetic energy that we require is something that equals, at least in magnitude, the amount of gravitational potential energy. So you can write it in a statement like this. And if you write it like this velocity actually has a name, we call it the escape velocity, and you can solve for it, and this will give you this answer. That's square root of 2 gm over r. And it turns out that the escape velocity is essentially square root of 2 times the velocity you need to be in a bound circular orbit, where the bound circular orbit is simply square root of gm over r. There are, of course, important considerations, such as the fact that the escape velocity does not depend on small m. It only depends on the mass of the body you're trying to escape from. And essentially, the fact that when you achieve or exceed the escape velocity, your orbit will no longer be an ellipse. It will either be a parabola or an hyperbola, depending on the energy that you're actually injecting, or the total energy of the system, really. Now, in the lecture notes, you have lots of examples of how to calculate the escape velocity from the Earth's surface and how to get the typical value of 11.2, but also how much energy you would actually need if you want to send, say, a sports car to space with some considerations, including how much that would cost, even if you could just send this car straight away without considering the rocket. How to calculate the escape velocity from the sun, essentially if you want to send something away from the solar system, and also some considerations about the cost. And there will be similar problems in the first worksheet. Now, one of the things that is worth mentioning is to try to kind of put orbits into a wider context. If we look at this expression of the classical total energy of a system, we can also further write it in terms of these three different components. Essentially, what we're doing is we're splitting the kinetic energy in terms of a radial component and a tangential component, and we're keeping the gravitational potential energy. What this allows you to do is to also re-express the tangential component. So we're keeping the radial component as in the normal form, and we're re-expressing the tangent component in terms of angular momentum. So we can do this by recognizing that the orbital angular momentum will just be given by rm and the tangential velocity. And some important considerations include the fact that this middle term that you can see here is the potential energy that is associated essentially with the angular momentum of the orbit. This L square over 2mr square that you can see, this is the middle term, it will dominate at the smallest r. That is because it is a term that depends on 1 over r squared. When r becomes very small, it is a term that will actually dominate. And it turns out that the term that dominates at larger r is a gravitational term. So it is possible to actually redefine this UR, and we'll see why this might be useful to classify orbits, as essentially these two terms. So we'll keep the other one as the pure kind of kinetic energy to do with the radial velocity, and we'll redefine this as UR. And if you do this, essentially it means that the particle, the object, the planet is moving in an effective potential. So you could see this as a potential UR, and the nature of the orbit will be dependent on the total energy, whether this total energy is positive or negative, and also the actual value can make you predict whether you are orbiting in a circle, an ellipse, in a parabola, or an hyperbole, for example. And this is what we can see here. And essentially, we have three different cases. So if you're experiencing the minimum possible energy, then you are definitely in a closed orbit that is a circle. The circle corresponds to the minimum energy of this UR versus R that you can see here. If you're in the very minimum here, you are in a circular orbit. If you have a negative energy, you're always in a bound or closed orbit, and that is an ellipse in general. This means that your eccentricity will always be below 1, and you have sort of a general orbit. Once you achieve an energy of 0, then you start having an open parabolic orbit with eccentricity of 1. You achieve this if your velocity is exactly the same as the escape velocity. And if you exceed the escape velocity, then you have even higher eccentricities, and you have definitely an open orbit. And you can also see how these different orbits compare around here, from going to a circle, to an ellipse, to a parabola, and an hyperbole. So this means we have a very simple way to, from physical considerations of the total energy and the different components, whether an orbit will be closed or open, and also what its geometrical meaning will be, just based on this total energy.